Quantum computing is entering a new era. The pace of development has quickened, and there's a growing hope that the next 10 years could finally bring us machines capable of solving intractable problems, like predicting chemical reactions or cracking complex encryption. But how can a quantum device solve problems a conventional machine cannot? And what even is a quantum computer? Classical computers, like the device you're watching this video on, work by encoding data in bits. Bits are units of information that can read 1 or 0. Quantum computers use a different kind of bit, qubits. Qubits can read 1 or 0 too, but also a continuum of possibilities in between. This is called a superposition of states. Qubits can be part 1 and part 0 at the same time, and these qubits can become entangled, a property that intrinsically links the states of the entangled qubits. This entanglement allows quantum computers to manipulate multiple qubits at once and leads to an exponential growth in computation. So, if you took 2 of these entangled qubits, they could be in one of 4 special states: 0, 0, 0, 1, 1, 0, and 1, 1, no different to regular bits, but they could also be in a combination of those states. Quantum computing works by taking these superposed qubits and performing simple manipulations on them called gates. These gates put the qubits into a new state, and qubits will go through a long sequence of them as part of a quantum computation. Finally, that state can then be measured, at which point the qubits superposition collapses and it gives a digital answer, 1 or 0 again. This might sound a lot like regular computing, but there's a key difference. At any point during the process, these qubits are a combination of all 4 possible states. And that means that you are effectively doing 4 calculations at the same time. That's 4 times the computation of a classical computer. It's called quantum parallelism. You can't extract all this information, but you can design an algorithm so that what you can measure provides a meaningful result. And all this makes quantum computers not only incredibly powerful, but also with huge potential to grow. For example, if Moore's law states that computers can double in power and memory every 2 years, for a quantum computer, you could do that by adding just 1 extra qubit. But there are some big problems. First, quantum states tend to randomly drift. After a certain amount of time, any information they stored is inevitably lost. And second, even the simplest of manipulations or measurements has a chance to introduce errors. In quantum computing, things don't always work out as planned. What's got scientists excited now, though, is that researchers around the world are starting to show that these problems are solvable. The technique they've developed is called quantum error correction. It takes a single unit of quantum information, called a logical qubit, and spreads it across several entangled physical qubits. If it works, the process can reduce errors by as much as is desired. But this isn't a panacea. For a long time, scientists estimated that using this method to run a fully fault-tolerant quantum algorithm would require an overhead of 1,000 to 1. That means 1,000 physical qubits for each logical qubit. The largest quantum computers built so far have just a few thousand qubits, and early estimates suggested that billions might be needed to solve the problems that quantum computing has in its sight. So, improving the efficiency of quantum error correction has become the name of the game. And there are several possible approaches, techniques that encode the information of a logical qubit more efficiently could be developed. And improving the quality of physical qubits and the accuracy of gate operations means that fewer error correction steps will be needed. Developments like these have already seen the number of physical qubits needed for the most exciting applications drop by roughly an order of magnitude every 5 years. Recent breakthroughs have shown that just 100,000 qubits could be enough, or even fewer. This improved efficiency could mean that it will take a much smaller number of qubits to make a fully error-corrected quantum computer. In fact, these machines could be here in the next 10 years.